Welcome to Dr. Boxy Teaches Probability Theory and Statistics. In the previous lesson, we introduced the notion of a probability measure, which is the mathematical way of defining the word probability, and then we looked at some of its properties and applications. Today I want to continue that discussion. I will first introduce a principle known as the principle of multiplication, and then we will look at concepts known as permutations on the one hand and combinations on the other. So let us get started. We consider an experiment in which we throw two dice. One is a normal die, one with 6 sides, and another one is a special one with 4 sides. The combined experiment of throwing both dice, how many possible outcomes does it have? The answer is 24, 4 times 6. Why is that so? Well, one way to understand why that must be true is to write all possible outcomes for the 4-sided die and for the 6-sided die and represent them in matrix form. So you have a matrix with 4 rows. Each row corresponds to one of the outcomes for the 4-sided die and 6 columns corresponding to each of the outcomes of the 6-sided die. And every position in this matrix corresponds to one possible outcome to this experiment. So in this case, the number of possible outcomes is 24. More generally, if we have an experiment that has m possible outcomes and another one that has n possible outcomes, then the combined experiment has m times n possible outcomes. This principle is known as the multiplication principle. This can be generalized in a straightforward way to more complicated cases. So imagine now that we don't have 2 experiments, but p experiments. The first one has n sub 1 possible outcomes, the second one has n sub 2 possible outcomes, etc., all the way to the pth one, which has n sub p possible outcomes. And the combined possible number of outcomes for the whole set of all experiments together is n1 times n2 times n3, etc., all the way to np. This is known as the extended multiplication principle. And we can look at an example of this. In computers, information is stored in bits. Each bit is a piece of information that can take one of 2 values, which is usually represented by either a 0 or a 1. And we usually collect them together in pieces of data known as bytes, and a byte is simply a collection of 8 bits. That means that if I look at such a byte, it's actually a box containing 8 bits. So this is box number 1, box number 2, box number 3, and so forth, up to box number 8. So this is one byte, a collection of 8 bits, and each of those boxes, each of those bits can take on a value of either 0 or 1. The question is, how many possible bytes can we make here? Well, we can consider this as 8 consecutive experiments in which each of those boxes corresponds to an experiment, and the outcome of the experiment can either be a 0 or 1. Well, the first box is the first experiment, and it can have one of 2 values, either 0 or 1, so there are 2 possible outcomes here. For the second box, we also have 2 possible outcomes. For the third one, we have 2 possible outcomes, etc., all the way to the 8th one, which also has 2 possible outcomes. In other words, the number of possible bytes that we can create is, according to this multiplication principle, 2 times 2 times 2 times 2, the number of possible outcomes for each of the experiments individually, and then just multiplying them. So that's 2 times 2 times 2, and this is 8 times, which is 2 to the power 8, which is 256. So it turns out, using 8 bits, we can have 256 possible values for a byte. We now introduce the notion of a permutation. So what are permutations used for? Well, we look at a situation in which we have n objects and we want to place them in n boxes in some order. And the question is, how many possible arrangements are there for those n objects in n boxes? It's the same question as if you have 5 people sitting on 5 chairs. How many possible seating arrangements are there? Well, how can we try to figure this out? Well, I made a figure of those n boxes here. And for the first box, how many possible choices do I have to choose one of those objects and put it there? Well, for the first box, I have n possible choices. But once I made a choice, I picked one of those objects and I put it in that box, I'm left only with n-1 object remaining. So for the second box, I only have n-1 possible choices that I can make. For the third box, I then have only n-2, etc. And you can keep on doing that until for the last box, you only have one single option left. According to the principle of multiplication, the number of arrangements would just be n times n-1 times n-2, etc. all the way to the last box, which is times 1. And this is written, a shorthand notation for this multiplication is n factorial. So for instance, the example I gave at the start here, you have 5 persons and 5 chairs. How many seating arrangements are there? Well, the number of arrangements is, according to what we saw here, equal to 5 factorial, which is 5 times 4 times 3 times 2 times 1. 5 times 4 is 20, times 3 is 60, times 2 is 120. Apparently, for 5 people in a row, there are 120 possible seating arrangements. The concept I introduced on the previous slide is known as a permutation, but there is also something known as a partial permutation. In this case, we once again look at n objects, but we only have k boxes here, where k may be less than n. So an example of this would be the game of musical chairs, in which you have some number of people, but there are fewer chairs. You still can ask the question, how many seating arrangements are there, but not everyone may get to sit down. And so how can we calculate or reason a formula for this, find a formula for this? Well, here are the k boxes. And for the first box, I have n possible choices, n possible objects to choose from, so I have n options. Once I made a choice for the first box, I have n-1 choices for the second box, afterwards n-2 for the third box, etc. Now, notice the pattern here. For the first box, what I had, the number of choices I had was n minus the number of the box, so 1 plus 1. For the second box, I had n minus the number of the box, so that's n-2 plus 1. For the third box, I had n minus the number of the box, so n-3 plus 1. So what is the pattern here, where every time it's n minus the number of the box plus 1. And so for the kth box, I will have n minus k plus 1 possible outcomes. Now the principle of multiplication tells me that the number of arrangements you have is simply the multiplication of these numbers. So it's n times n-1 times n-2, etc. all the way to n minus k plus 1. Now this is the number of arrangements we have. I just want to rewrite it in a more elegant way. And what I will do is I will take the expression we had and multiply it and divide it by some number. But by doing it this way, notice what we get. In the numerator, we already had n times n-1 times n-2, etc. and it went all the way to n minus k plus 1. But then it continues now in the numerator. After n minus k plus 1, the next one is n minus k, then n minus k minus 1, n minus k minus 2, etc. all the way to times 1. So in the numerator, we're actually left with simply n factorial. What are we left with in the denominator? Well, we have in the denominator n minus k times n minus k minus 1 times n minus k minus 2, etc. all the way to 1. So this is n minus k factorial. And so this is the expression for the number of arrangements for a partial permutation, where you have n possible objects but only k boxes. Notice also that if the number of boxes k is equal to n, then we have in the denominator, numerator is n factorial, the denominator is then n minus n factorial, which is 0 factorial, and 0 factorial is by definition equal to 1. So we get n factorial, which is the same expression we found for a full permutation, which we saw on the previous slide. As an example of this partial permutation, I want to look at the example of the musical chairs I described on the previous slide. So the number of arrangements is n factorial over n minus k factorial. And if, let's say, we play musical chairs with 8 people, so you have 8 persons, but only 5 chairs. How many seating arrangements are there? Well, according to the expression we just found, it would be 8 factorial divided by 8 minus 5 factorial, which is 8 factorial divided by 3 factorial, which is 8 times 7 times 6 times 5 times 4. Notice that the 3 to 1 in the numerator cancels with the 3 to 1 in the denominator. So this is the result for the number of arrangements there are. And if you plug this into your calculator, you find that there are 6,720 possible seating arrangements if you want to seat 5 people out of the 8 possible people on those 5 chairs. We look now at permutations without repetition. What I mean is, once we used an object in one of the boxes, it wasn't available for use in a next box. But there are situations where you want them to be repeatable. For instance, if we think of a pin code is usually constituted of 4 numbers. So that's 4 boxes. And in each of the boxes, we can choose any of the digits, any of the numbers from 0 all the way to 9. So each box has 10 possible choices. But let's say that I chose as the first number, the number on the first position of my pin code. If I chose that to be an 8, nothing prohibits me from reusing the 8 again. And so in this case, there is repetition possible. What happens then to the formula of permutations? Well, we once again have n objects and k boxes, but this time I have, for the first box, n possible choices. But no matter which choice I made for the first box, I still have n choices for the second box, and still n for the third, and for the fourth, etc., all the way to n for the kth box. And so in total, the number of arrangements is n times n times n k times. In other words, it's n to the power k. So for the pin code example I gave, I need 4 numbers. Each of the numbers is any number between 0 and 9. In other words, there are 10 options. And so the number of possible pin codes you can create using 4 positions is 10 times 10 times 10 times 10. That is 10 to the 4th power, which is 10,000 possible codes. There is a fun application of what we've seen until now, and that is the following question. If I take k people and I put them in a room, I can ask myself, what is the probability that at least 2 of them have a birthday in common? And the question becomes, how high does k have to be for this probability to be 50% or higher? Well, the answer may surprise you. So let's see if we can calculate it. Well, the sample space is the set of all the days in a year. And to make our life simple, I will forget about leap years. So there are 365 days in a year, so 365 elements in the sample space. And I will assume that the probability of having a birthday on each of those 365 days is exactly the same one. In that case, we know that we're allowed to use the formula that I wrote now at the top right of the corner, which is the probability of some event is the number of ways in which that event can occur divided by the total number of possible outcomes. The event A that we're considering in this case is the fact that at least 2 people share a birthday. Now, how can we calculate it? Well, what we do is the following. We know that the probability of A can be written as, in this case, it's easier to do it this way. We saw last time we can calculate it as 1 minus the probability that A does not happen, so the complement of A. So that is 1 minus. Now, what is the probability of the complement of A? That means that nobody in the room shares birthday? Well, if I have k people, the total number of outcomes is each person has 365 possible days that they have their birthday on, and they may be the same, they may not be. For one person, there are 365 possible outcomes. For two people, there are 65 times 365. For three people, you multiply it again with 365 and so forth. In other words, for k people, you have in the denominator 365 to the power k. In the numerator, what you want is that the people don't have the same birthday, because we're looking at PAC in this case, so that's the probability that nobody shares a birthday. That means the first person has 365 possible days that they can have their birthday on. The second one can only have 364, because you don't want that second person to share his or her birthday with the first person. The third person cannot share it with either the first or the second, so he or she only has 363, etc. So this is a partial permutation where in the numerator you have 365, and in the denominator you have 365 minus k factorial. This was the formula for a permutation, a partial permutation, when there is no repetition. And the fact that we don't want them to share a birthday means there is no repetition here. Now, you can calculate this for different values of k and see what you get. I did that, and here is a table with the result. The left column is k. And notice that the 50% is reached once we have 23 people in the room or more. So that may seem counterintuitive because there are 365 days. How can it be that once there are 23 people in a room? Well, just do this calculation, you'll see that's correct. And so it's lower than you might expect. But there is a slight variation of this question, which makes it even more interesting. And that is the following one. How many people do you have to ask before you have a 50% chance or higher of finding someone who shares your birthday? So once again, you are going to ask k people, and the event A in this case is that somebody shares your birthday. Now, once again, what I will do is calculate the probability that someone shares your birthday by calculating 1 minus the probability that they don't. So AC is in this case the fact that nobody shares your birthday. So that is 1 minus, and once again, I use the formula that I wrote at the top right of the slide. What is the probability that nobody shares your birthday? Well, in the denominator, the total number of outcomes, if I ask k people, is again 365 times 365 times 365, etc. k times, so that's 365 to the power k. But now in the numerator, I want to count the number of ways in which A can occur, A cannot occur, so AC can occur. How many ways are there? Well, the first person that I approach, he or she can have any of the 364 days in the year where I don't have my birthday. They can have that as their birthday. The second person I go and ask can also have 364 days as their birthday, as long as it's not the one day on which I was born. The third one again still has 364 days, etc. So if you ask k people, you have a 364 to the power k here. And once again, this is now the expression you have. You can calculate this for different values of k and see what you get. And the result is the following one. Notice, first of all, that when you ask 23 people, you are way below 50%. We reach the 50% only when we ask that question to 253 people. So significantly more than half the number of days there are in a year. Even more than that, there are only 365 days in a year, but even when I ask 400 people that question, there is still only a 66% chance, 67% chance that they share my birthday. How can that be? Well, there are 365 days, of course, but there is nothing that prohibits them to have a common birthday among themselves, between themselves. If I ask 400 people, most certainly some of them will share their birthday. It's simply the difference between the question I asked here and the question on the previous slide is that on the previous slide, it can be any day that they share in common. I did not choose beforehand which day I want them to share the birthday. I just want to have some pair within the group of K people, some pair that shares a birthday. In this version of the question on this slide, I beforehand already decided I'm looking for a person who shares a specific date, namely my birthday. And that makes the calculation different, and we get a very different result, which may, in this case, seem higher than you might have expected it to be. The final concept I want to introduce today is the concept of a combination. Now, what do we have in mind here? We have 7 people, and we want to build a team existing of 4 out of those 7 people. How many possible teams can we create? Well, it may seem similar to what we had before. You have n objects, in this case 7, and you want to choose k out of them. The difference between what we did before and now is that the order in which you choose them does not matter. Imagine that the team I create, I will represent it by a box with 4 smaller boxes in it. And the team I can create could, for instance, be Bob and Fran and David and Alice. But I could have created the same team by choosing those same 4 people, but in a different order. So for instance, Fran first, then Alice, then David, and then Bob. The team is still the same team. It's the same 4 people. I just chose them in a different order. But if all you're interested in is who sits on the team, the order in which I chose them does not matter. And that is why we need to adjust the expression we have mathematically compared to what we had with permutations, where the order did matter. So if we were to say that the order does matter, then we know what the answer is, namely n factorial over n minus k factorial, which in this case would mean it's 7 factorial over 7 minus 4 factorial. This would be the answer if the order did matter. But in this case, the order doesn't matter. So that means that I overcounted all the possible ways in which I can choose those same 4 people in any order there is. So that means that the factor by which I overcounted it is the number of ways I can reorder these same 4 people. But because I chose 4 people, the number of ways I can reorder them is a permutation of 4 objects. So that's 4 factorial. So I'm adding a 4 factorial in the denominator. That means in the expression for a combination, what I have here at the bottom of the slide, we have n factorial over n minus k factorial. That would be the case for a simple permutation, partial permutation. But now we overcounted it by the number of ways we can rearrange those k choices, those k objects that we did choose. And that means that there is an additional k factorial we have to add in the denominator. And this expression is written shorthand using this symbol, and it's known as a combinatorial factor. Finally, I want to show you an example of an application of such combinations. If you play the lottery, you have to choose 6 numbers out of a possible 49 numbers, and you win the jackpot if you chose the 6 correct numbers. So let us say that A, the event A, is winning the jackpot, meaning you actually chose the 6 correct numbers. Now, how many options are there for you to choose from? Well, there are 49 numbers, so n is 49, and you need to choose 6 of them, so k is 6. What is the probability to win? Well, it is in the numerator the number of ways you can win, but there's only one way to win, namely circle the 6 correct numbers. And in the denominator, it's the total number of possible choices you have, which is a combination of k out of n, so 6 out of 49. So that means that that is equal to 1 divided by 49 factorial over 49 minus 6 factorial times 6 factorial. And if you calculate this, what you find is that it is approximately equal to 1 over almost 14 million, which is a tiny, tiny number. And that may be part of the reason why Very few mathematicians play the lottery. This was what I wanted to discuss with you today. In the next lesson, we will introduce the notion of conditional probabilities, and we will look at the concept of statistical independence. I'll see you next time.